Back in 2017, one single research paper dropped and it completely changed the game for artificial intelligence. You've probably heard of it. Attention is all you need. This paper is the reason we have the incredible language models we see today. So in this explainer, we're going to break down the revolutionary ideas that made it all possible. It really all boils down to this one question, right? How did we leap from clunky chatbots and awkward translations to AI that can write code and poetry? Well, the secret is that they had to completely throw out the old rulebook. Now, to really appreciate just how big of a breakthrough this was, we first have to understand the problem they were trying to solve. For years, AI was kind of stuck behind this huge roadblock, what's known as the sequential bottleneck. See, before 2017, the top models were something called recurrent neural networks, or RNNs for short, and they were designed to process language the same way you and I read a book, one word at a time, in order. And that sounds logical, right? But it turns out that was a massive, massive problem. Think about it. The old way was just slow, plodding along word by word. This made it incredibly difficult to train on huge amounts of data, and it made it almost impossible for the model to connect a word at the beginning of a long paragraph with one at the very end. The new way, though, it's a parallel approach. Bam! It sees every single word at the exact same time, which solves both problems in one fell swoop. So the bottom line was that the very design of these older models was holding back progress. The paper itself calls this inherently sequential nature a fundamental constraint. AI was basically stuck in this one word at a time prison, and it needed a jailbreak. And that brings us to the solution. This paper from a team of researchers at Google that proposed a totally radical new architecture. I mean, just listen to this line from the paper's abstract. This was a thunderclap in the AI community. They weren't just tweaking things. They were proposing to throw out the entire foundation, the recurrence and convolutions that everyone was using, and replace it all with one single powerful idea: attention. And this new attention-based architecture was called the transformer. It came from Ashish Vaswani, Noam Shazir, and their colleagues at Google, and it was a complete rethinking of how a machine could understand language. Okay, so what is this magical attention thing that replaced everything? Let's break it down. It's actually a really elegant way for the model to figure out the importance of different words when it's looking at a sentence. The paper calls the technique self-attention. In simple terms, what that means is, for any given word in a sentence, self-attention lets the model look at all the other words in that same sentence and decide which ones are most important for understanding that one specific word's context. Let's use an analogy to make this super clear. Imagine each word in a sentence is a person at a party. First, each word creates a query. You can think of this like the word asking a question. For example, the word it might ask, hey, to understand what I'm referring to, who here at this party should I be paying attention to? So in response to that question, every other word in the sentence generates a key. The key is kind of like a name tag that says what kind of information that word has. A word like robot might have a key that says, hey, I'm a noun, a physical object. A word like kicked might have a key that says, I'm a verb, an action. All right, finally, the model matches the query from our original word it against the key from every other word. A high match score means that word is super relevant. The model then takes each word's value, which is its actual meaning, and weighs it based on those scores. And the result? The word it is no longer just it. It's now this new, richer version that knows it refers to the robot. And the incredible part is, this happens for every single word, all at the exact same time. So self-attention is the heart of the transformer for sure, but the full architecture has a couple of other brilliant ideas that really make it sing. Instead of just calculating attention once, the transformer does it multiple times in parallel. They call this multi-head attention. In the paper, they used 8 of these heads. Think of it like having 8 different experts read a sentence at the same time. One expert is just focusing on grammar, another on who did what to whom, and a third on the overall theme. By combining all those different perspectives, the model gets a much richer, more nuanced understanding of the text. But hold on a second. If you get rid of that word-by-word processing and look at everything at once, you create a new problem. How does the model know that the dog bit the man is different from the man bit the dog? The words are the same. The solution is just so clever. Positional encoding. Before any of this attention stuff happens, the model adds a little mathematical fingerprint to each word that signals its original position in the sentence. It uses sine and cosine waves to do this, which have these beautiful predictable patterns. This means the model doesn't just know a word's position, it can easily figure out the distance between any two words, giving it a powerful sense of order without ever needing to read one word at a time. So you put all of this together. You have this new architecture that can process words in parallel and understand context on a really deep level. What was the result? Well, it kicked off a completely new era for AI. This table from the paper just says it all. If you look at the top row for the old models, you see that both the number of steps and the path to connect words gets longer as the sentence gets longer. That's what O of n means. But now look at the bottom row for self-attention. It's constant, O of 1. It doesn't matter how long the sentence is. This is a night and day difference in efficiency. And it all adds up to this amazing triple win. The transformer architecture is way faster to train, it's perfectly built for modern computer chips, like GPUs, and it's fundamentally better at learning the relationships between words, no matter how far apart they are. And this wasn't just theory, right? The proof was in the pudding. The results were immediate, and they were dramatic. On a standard benchmark for machine translation, in this case English to German, the transformer model got a blue score of 28.4. Now, 28.4 might just sound like a number, but this chart shows why it was so mind-blowing. You can see here that the previous best models, which were these complex mashups of different systems, they topped out right about here. The transformer didn't just squeak past that record, it smashed it by over 2 full points, setting a completely new state of the art. And this just brilliantly sums it up. The model wasn't just better, it achieved that brand new record while taking, in their words, significantly less time to train. Better, faster, and cheaper. I mean, that is the hat trick that every single field of engineering dreams about. This 2017 paper laid a whole new foundation for AI. Seriously, every major large language model you've heard of today, from BERT to GPT, is built on top of the transformer architecture. It truly was the moment that unlocked the AI revolution we're living through right now. Which really makes you wonder, if this is what happened when attention became all we need, what on earth comes next?